In this module, we're going to talk about how we integrate ACI in with traditional layer 2 networks. We'll talk about why you would want to do that. We'll talk about some options, whether or not to use a contract or not use a contract to govern the communications between the ACI fabric and that outside layer 2 network. We'll talk about design considerations such as spanning tree protocol and MCP, as well as common deployment and migration strategies that are often used when migrating to ACI.
All right, let's talk about why we would want to do an L2 extension beyond the ACI fabric. So there may be cases where we have existing bridge domains, EPGs, VRFs, etc. for a given tenant. Here we have tenant blue. And we need to connect to legacy equipment. We need to connect to non-ACI infrastructure. For example, if we still have a 7K, 5K, 2K stack, or a 9K stack running in NXOS mode, or switches from another vendor, then we're going to need to be able to extend connectivity from a bridge domain or from an EPG out to those switches. And to do so, we can do we've got two basic choices. We can do so by connecting statically to an EPG. This does not require a contract between an external VLAN and this EPG. It still does require a contract between this and other EPGs, but we're basically extending an EPG out into an external layer 2 device. The other way is to use an external bridged network. So this creates a new EPG for this layer 2 network, and a contract is required between the EPG inside ACI and this external EPG. So we've talked about L3 outs before, so this is an L2 out. So an L3 out is a layer 3 outside network, such as 0/0 for the internet. And the L2 out is an external layer 2 network that we're connecting. So we've got those two choices, and either one will make sense depending on what your needs are. So option number one, we're going to use an EPG. So in this case here, we've got an EPG web, and we've got a VM attached, because it's attached to a hypervisor, or maybe it's a bare metal system, and it's attached directly to a leaf. So we don't have any problem there. It's just a native EPG. But we have these other two virtual machines, or these other two hosts. They're plugged into an external layer 3 infrastructure or layer 2 infrastructure. For example, these two might be 7Ks and these are 5Ks, or maybe these are 5Ks and these are 2Ks. But either way, we've got intermediary devices in between our ACI fabric and these hosts. So what do? Well, for one thing, we're going to create a back-to-back VPC, sometimes called a bow tie. So these two switches are acting as one, these two leaves are acting as one. So it's basically a single VPC between two switches, even though there's four. And we call this a bow tie sometimes. We're going to use a VLAN, and we're going to map that to that EPG. So in this case here, we've created VLAN 10. We're going to trunk it to these ports here. On these switches, on their VLAN database, or whatever the equivalent is for that platform, we're going to trunk VLAN 10 up to these links, and then down to these VMs here, and that will extend VLAN 10 out to these switches and add it to that EPG. So we're extending an EPG beyond the ACI fabric. No contract is needed within the EPG. Endpoints do not need to be directly connected to that ACI leaf. That's the advantage of doing it this way. It's one of the things of why we would want to do these external EPGs or layer 2 outs, is because we have devices that are not directly connected to an ACI leaf port. BDPUs for spanning tree are always flooded within an EPG to help out loop prevention. So to do this in the API controller, we would assign ports and endcap to an EPG, which I'll show you in just a second. We're going to create and use a physical domain and a VLAN pool. This will be a static VLAN pool because we're doing static assignments. We don't have an orchestration going on like we do with vCenter and the API controller to do this. So we're just going to assign a VLAN statically. We're going to associate that EPG with that domain. We're going to map a domain to an attachable entity profile and to the interface policy group for the port numbers. So here's what it looks like under static paths. We've got, so this is under an EPG. We've got VLAN 200, and we're trunked, and that's connected to pod 1, node 101, so this is the leaf ID, and interface 11 on VLAN 200. So what it looks like here is we use a static binding. So here we have tenant T03 under application profiles, under web app, under application EPGs, under our database EPG, under static bindings, right click, deploy static EPG on PC, on port channel, virtual port channel interface. So here we're just doing interface on node 101, Ethernet 1, interface 1.2. We're going to do VLAN 200. Deployment will be immediate or on demand, doesn't matter which, or it doesn't matter which, depends on what your needs are. I just picked immediate here. And then we've got trunk access 802.1p and access untagged. So what does it mean? What do we mean by trunk 802.1p and access untagged? Trunk and access untag are pretty self-explanatory. One's a trunk port, just like a switch port mode trunk, and the other one is access, like switch port mode access. The difference: trunk throws the 802.1q VLAN tag on each Ethernet frame. Access means it's untagged. 802.1p means we're throwing a VLAN header on, but there's no VLAN ID. But we are including the 802.1q. So this is a native VLAN when we're throwing the 802.1q header on there, so that we can, with no VLAN IDs, so that we can use the cause value field, such as cause. We have cause 0 through 7 that we can use. 6 and 7 are typically reserved for control plane traffic, so we've typically got 6 cause values we can use in order to use for QoS, for at least for layer 2 marking. And this screenshot here is from the 1.0 code. It looks very similar in the 2.0 code, but under endpoint, we'll see the MAC address of the endpoint. We've learned it through control plane, or through data plane rather. And the interface is, in this case, node 17. So that means its leaf ID is 17, Ethernet 1.5, and VLAN 10 for the encapsulation. Option number 2, use an external bridge network. So we can extend a bridge domain to an external VLAN or VNID. So VNID would be VXLAN. So packet forwarding between the EP in a bridge domain BD1 and external hosts on VLAN 500 is an L2 bridge. So in this example here, got a little bit backwards here, but it doesn't matter for this example. We have our web EPG here. We've got our application EPG here. We've got an application network profile under bridge domain BD1. Here we've got our web tier, we've got our app tier, although these are switched. They should be reversed, but it doesn't really matter. The front end connects via contract into the mid-tier. The mid-tier connects to the database layer. In our case, we've got a database. Maybe this is a legacy database server. It's connected to some legacy switches. So we need to extend connectivity through an external layer 2 network so that we can protect this. We can do forwarding and policy enforcement for this physical host, even though it's not plugged directly into the ACI fabric. So what we're going to do is we're going to do an L2 extension using a VLAN tag. So we're going to use VLAN tag 100, so VLAN ID 100. We're going to tag that to this port, trunk it down. This switch is going to have VLAN 500 in its VLAN database. It's going to be trunked up here, and it's going to be probably an access port here. It's not impossible for a host to send out tagged frames, but typically they just send untagged frames or act like an access port. But this will allow us to extend that domain through, so we can build a contract between this L2 external EPG. Again, this is an L2 out, kind of like how we have an L3 out. L3 outs are defined by their subnet mask. L2 outs are defined by their external connectivity through typically VLANs, although it could be a VXLAN. So the workflow is we create a bridged outside network. We assign ports and endcap to that bridged outside network. We create an external EPG. We create an external bridge domain and a VLAN pool. Again, it'll be typically be static VLAN assignments. Since we're not using an orchestrator, we're going to assign the EPG to the extended bridge domain. We're going to map that domain to an AEP and to interface policy group for port IDs, and then we're going to create and assign the contract for that external EPG. This external EPG, just like an internal EPG, can both provide and consume contracts. So we go under networking, under external bridge networks. We'll right-click and create a bridged outside network, give it a name. We're going to create a new external L2 domain, and we'll use the bridge domain. For example, this is tenet3, the database bridge domain, and then pick an endcap. We'll also pick a profile a node profile. So this is port, and then the path is going to be pod 1, node 102. So this is leaf 102. So we're not doing a port channel or VPC on Ethernet 1.2. Design considerations. One thing to keep in mind is that the ACI fabric is not running spanning tree inside the fabric. That's the whole point. That's one of the points of ACI, is to get away from spanning tree. But we may have a situation where we're plugged into two different switches, and we have potentially a bridging loop going on. So a BDPU frame is flooded within an EPG. So let's say these two ports are configured for the same EPG. Because we're flooding the BDPUs, the spanning tree protocol will determine that there is a redundant path here, and then shut down one of these interfaces on the switch here. So this is as if they were plugged directly into each other from a spanning tree perspective. And remember, spanning tree is there. The problem isn't spanning tree. The problem is in Ethernet networking in layer 2, we have that golden rule: never be let there more than one way to get anywhere. So spanning tree is taking a look at the network. We've got the root bridge, and we're building a tree from the root to make sure that we don't have redundant paths down to any given host. So never let there be more than one way to get anywhere. And by flooding BDPUs, the bridge protocol data units inside of an EPG, then the switches can detect each other and then block that path. So a BDPU is always flooded within an EPG. An access policy can be created to enable BDPU filter and BDPU guard on selected ports. Data traffic flooding can be turned on and off on per bridge domain level. If you're extending your layer 2 out, you're typically going to want to turn on layer 2 flooding. So rather than do the directed broadcast and so forth. So it's important to turn on BDPU guard on the edge ports. One thing, so we're not sending across the bridge domain. All right, let's talk about the miscabling protocol, the MCP. So there's a couple of situations where we can possibly create a topological loop that we don't need MCP. For example, here's an ACI fabric. We got two spines. We got two leaves. The leaves are TOR1 and top of rack number 2. We've plugged port 3 and port 4 into each other, and we've plugged port 1 and port 2 into each other. These are both prohibited by ACI rules. We cannot plug a leaf into a leaf. We cannot plug a spine into a spine. The only thing that we plug spines into is other leaves or the IPN if we're doing multipod, which we have a separate section on. From the leaves, we only uplink them into other leaves, or we only uplink them into spines, and we downlink them to end hosts such as layer 2 out switches, layer 3 out routers, hosts, load balancers, firewalls, etc. So we do not plug leaves into each other. In this case, if we did, we've got LDP or possibly even CDP. It detects the loop, shuts down the ports, puts them into error disable, no problem. Same thing if we plug a switch into itself, detects it through LDP, shuts down the ports, puts them in error disable, no problem. One case where we might need MCP is if we have an LDP disabled by our port policy group. So our policy group has LDP disabled or CDP disabled, and we plug them into each other. There's nothing preventing that loop from occurring. So that's a case where we might want MCP. We also might want MCP if we plug one switch into two different switches and they're not on the same EPG, then we can run into a layer 2 loop. So to prevent that, we can enable something called MCP. Now, MCP is disabled by default under Fabric, under Access Policies, under Global Policies, globally for the entire Fabric. MCP is disabled by default, so you can enable it. Paradoxically, if you go into under Policies, so we have under Interface Policies, we have Policies, we have MCP Interface. It is enabled here. However, if it's enabled here and disabled here, it's still disabled. So you have to enable it here once, and then the default for everything is enabled. So under default, this is the default MCP policy. We can do enabled. We put in a key. So what MCP is it sends out a layer 2 frame, and we have a key in there so that we know who we're talking to. And it detects, hey, I've got a layer 2 MCP frame. and I've got it from the other leaf, or I've got it from another port, so that it knows that there is a loop in there, so it turns it off. We've got a loop detect multiplication factor. Here we have 3, which basically means we have to see 3 of these frames and before we put that port into error disable. Or actually, loop protection action is port disable, so that's the default if we do enable it. If we turn this off, it just logs it and doesn't do anything. Doesn't put the port in error disable, just puts it into a log. We've got our initial delay, and this is typically for spanning tree, because spanning tree, as it detects, as it runs and detects topology, it might go into listening and learning state, and that might take even a minute or so in order for that to actually start forwarding, to get into the forwarding state. So we put in this delay here for when the port comes up and before we actually start listening to these MCP frames. And then our transmission frequency is how often do we send these MCP frames. In this case, we're going to do 2 with a multiplication factor of 3. We're going to detect a loop within about 6 seconds. And so we can also do it per VLAN. So we can send PDUs, the MCP PDUs, those layer 2 frames per VLAN. Default is not. So just because we enable it here, we go into our interface policies. The default is enabled. We can create a new one under our MCP policy. We can create a new policy, or we can use the default for our leaf policy group. So these are our interface policy groups. So we can enable it there on a policy group by policy group basis.